Hello, everybody. Welcome to our webinar on Newton's laws of motion with the Smart Cart. Just a couple of housekeeping things real quick. All of you are on mute right now, but we do encourage your participation through the chat. We will be monitoring it, and please ask questions as we go along. My name is Jonathan Hanna. I am a product manager here at PASCO, also do product development. And also joining me today, over in the corner from me, is Glenn Starkey. I'll let him introduce himself.
Welcome, everyone. Thanks so much for being with us today. My name is Glenn Starkey. I'm in the Professional Development Department, and I'll be assisting Jonathan today by monitoring the Q&A and chat panels. So we welcome your questions and feedback there.
All right. Thank you very much, Glenn. So we're going to cover 3 laws in 20 minutes. So this will be interesting. We'll see how this goes. Uh, by no means do we expect that you would do all of these in 20 minutes. This is just, to give you a nice little taste of what you can do with the Smart Cart in your classroom. Probably the things we go through today could easily cover a week, if not more, in the classroom. And we'll share some resources at the end of the webinar so you can get some more ideas and expand upon what we looked at today. So the PASCO Smart Card is a great tool for studying Newton's laws, because Newton's laws are all about understanding how forces work and how those forces affect motion. So the Smart Cart, just the cart by itself with its low friction wheels is very helpful for, studying motion. But we took it a little bit further by actually putting some sensors into the cart. And for forces, we do have a force sensor built in on the front. And within the wheels, we have an encoder that tracks the position of the cart and then in turn can calculate the velocity and acceleration. If you want to measure acceleration directly, there's also a acceleration sensor built right into the cart. But we're not going to touch that one today. We're just going to be focusing on the force sensor and the position sensor. Now, as far as Newton's laws go, many different ways to teach it. I prefer actually going in the reverse order, starting with Newton's third law, because I think it's good to have a nice understanding on how forces work before you start tackling how forces affect the motion. So that's where we're going to begin today. And to help us understand Newton's third law, we're going to use 2 smart carts. So I'm going to start off by connecting it to our SparkView software. So I'm going to go ahead and share my screen so that you can see SparkView. And there we go. And I'm going to go ahead and connect each of the parts to SparkView, give you a different view here. And I'm just going to go ahead and turn those on. So we'll go under our sensor data path. And you can see our smart carts right there. We also got a melting point apparatus. I'm not sure how chemistry got in here. All right, there's the blue cart, and we'll go ahead and do the red cart. Okay, and as you can see, we have a lot of measurements on this screen. In this case, we're only interested in force, so I'm going to just turn off those other sensors right now. You don't have to do this, but it just makes it a little bit cleaner. And even though I want to display both of these, I'm just going to stick with one force for right now because it'll make our setup a little bit easier. So you'll notice that it brings up a graph of the force sensor for the blue cart, but we want the red cart on there too. So I'm going to add another y-axis and select the red force from there. And now we can go ahead and graph force for both the carts. Another thing that's actually very useful on here is this alignment tool. So this will keep the axes aligned for both of those forces. And then you can see, like, if I do some dragging there, you can see that both stay in sync. Okay, now there's another thing that we want to do for setup. So if you'll notice on the smart cart, there is an arrow that indicates which way is positive for the cart. Now we're going to have the carts face each other, and you notice that the arrows are pointing in opposite directions. So SparkView is smart, but it's not smart enough to know which way the cart is pointed. So I am going to change the direction of one of those carts in the software. We just need to define one way as positive. I think I'll go ahead and define um, the blue cart's direction as positive. So I'll change the red cart, and that's really easy to do in SparkView. So I go down to the bottom here where it says red, force for red, and I'm just going to click change sign. So let's start off with just doing a simple pull forces between the two carts. And I'm going to change my view so you can see it from overhead because I think that might be a little bit easier. And I'm going to go ahead and put these hooks in each of the cart so we can do pulling. Okay. Now you could hook these together by the hooks, but I don't prefer to do that for a couple of reasons. One, if you hook it by the hooks, I mean, you could get some lateral forces on there that could damage the built-in force sensor. So usually what we recommend doing is connecting them by a string, or in this case, I'm going to use a rubber band. I like rubber bands because, I mean, you can see the forces being applied. So to start off with, I'm not going to have any forces on there because I want to zero this out in SparkView. I'm not sure how well you can see this on your screen, but right now the forces aren't exactly zero. Well, I'll go ahead and click on the zero button to make them, well, they're still not exact, but they're closer to zero there. And then we'll go ahead and start graphing. Okay, right now in SparkView, we're not really seeing any force being applied, which is what we would expect. So what I'm going to do here is, and let me bring this more into view. I'm going to pull on the blue cart, and let's see how that affects the force on the blue cart. And let's see how it affects the red cart. Okay. Well, we see actually it affects both carts, not just the blue carts. What about if I just pull the red cart? It's affecting both of those too. And not only that, it's equal and opposite. So this is a great demonstration to understand how Newton's third law works, where you have equal and opposite forces on two objects. Now, we don't have to just do pulling forces, because students might ask, what about pushing? Does that matter? And what's great is we can measure push forces too. Let's remove the hooks, and we'll put in one of the bumpers. The Smart Cart comes with two types of bumpers. We have a rubber bumper, which I'm going to use today, and also a magnetic bumper, which is great for collisions. Okay, so now we have those in there. Bring that into view. Okay, and yeah, let's go ahead and start recording data again. Both 0. I'm going to do the same thing. I'm going to hold the red cart in place and move the blue cart. Okay. Yes, we see the same thing again, matching up. Let's try that with the red cart. I know you're just gonna have to believe me here that I'm only pushing on the red cart, but I guess technically I'm pushing on both, aren't I? All right, so yeah, it works with pushing, works with pulling. Another interesting thing to look at, how does it compare to our first run? Well, you notice on our first run, the blue was positive, and now the blue is negative on the second run because we're applying force in the opposite direction. So, one last thing with Newton's laws is, and this is kind of a little bit more Newton's third law, and this is a little bit more complicated for students to understand. Is, well, looking at the cart, this red card right now, and I'm going to change my view on this. Are there any forces on this card right now? Well, many students might say, no, no, there's no forces, but we know better. We know there's forces here. So there's a force due to gravity that for the cart going down, but there's also a force, a normal force pointing up, equal and opposite on that cart. Now, unfortunately, this is not a smart track, so the track doesn't have any force sensors built into it, but maybe we can do something to kind of simulate that. So I'm going to put the red cart facing upwards like this, and then I'm going to put the blue cart on top to simulate measuring the forces as if it was on the track. So right now, yeah, we're approximately 0. So I'm going to try to get that on there as close as I can. Okay, so we can see that, yeah, when I put the blue card on there, it's registering a force, and the red card's also registering a force that's equal and opposite. So there are indeed forces in the vertical direction that are balanced, and which is a very important concept to understand when you're studying more of Newton's laws. So that wraps up for Newton's third law. So that gives a nice starting introduction to understanding how those forces work. So let's take this a little bit further now and look at how these forces affect motion. So we'll take a look at Newton's second law. I'm going to go ahead and restart SparkView for this. So we can have a nice clean slate. I'm going to also, we only need one card for this, so I'm going to go ahead and disconnect the actually I'll disconnect the blue card. So I'll make things a little bit easier. Okay, so now we have the red card. And let's see how motion is affected by force. So for motion, I'm just going to graph velocity right now. Actually, hey, we can graph force too. Let's try both of those. So as you can see from our SparkView screen, we have a graph of velocity versus time and a graph of force versus time. And I'm going to actually replace this with a hook, and actually have a hook on a string, and I'll show you why I have a hook on a string in just a moment. Now, the reason I have a string on here is because I want to apply a constant force onto this cart. And being human, I'm not really good at applying a really good constant force. So what can we use instead? Well, we can use a mass that's hanging over the track. So that's what I'm just going to do here is I'm going to put 20 grams on here, and I'm going to put the string over. And this is a very classic way to study Newton's second law of motion. Okay, so now we got a tension on that string due to the mass that's hanging over the track. So I'm going to just give some slack in that string so we're not applying any force right now. And let me give a different view so you can see this a little more closely. All right, so let's see. Let me go ahead and zero out that force sensor. Let's take a look at the velocity graph. Okay, right now we don't have any motion, and then I'll go ahead and gently let that go. All right. So taking a look at SparkView, I'm going to go ahead and use one of our multi-coordinates tools here. So at this point right here, that's when the cart started moving. And we're seeing that as a constant force is being applied, that we're getting an increase in velocity. So the velocity is changing, we're getting an acceleration. So that's pretty good evidence that a force applied to an object accelerates that object. Now, what if we change some of these variables? What are some variables we can change? Well, we can change the force, obviously, that's one thing. We could also change the mass of the object, but let's start with the force on the object. So changing the tension in the string. So I'm going to add a little bit more mass to this. I'll add another 20 grams um, to the force over to the mass that's over the string to the multiply the force. And let's just take a quick note of some of those values that we have there. So looks like we got about zero point 0.2 newtons for the force, and we also have about 0.509 meters per second for the velocity. Actually, we probably shouldn't be doing velocity, should we? We should be doing acceleration. Let's try that again. Okay, scratch that with the velocity. Acceleration is 0.636 meters per second squared. Now I am being a little sloppy here because it's probably better to take the average of that flat section, but we only have 20 minutes here, so I'm not gonna be doing perfect experimentation right now. But, yeah, keep those numbers in mind or write them down, probably even better. And I'm gonna go ahead and double the mass hanging over. Let's see what effect that has on the acceleration. Oh, and I'm gonna keep it loose. Alright, and looking at that again, so now we got about 1.2, 34 meters per second squared, so about double. And, let's see, the force in that case, yeah, this is where averaging would be better, but, yeah, it's about zero point 0.3 or so, so not quite double, but it did increase. So, I mean, if you do this over and over, you could see that an increase in force correlates to an increase in acceleration. And if you're going to be a lot more careful, then you would also have try to see if there's a linear relationship to that. Let's do one more, adding a mass. So, what does that do to the acceleration? So, we'll keep note on this that we have about 1.2 meters per second squared for the acceleration and about zero point 0.3 for the force, zero point 0.3 newtons. All right, let's see what happens now. Same force, but more mass. So in this case, the force is about the same, but why is my acceleration this? That's interesting. That was kind of unexpected there. Let's uh let's add some more mass. Let's try that again. Okay, so now we got a little bit of a smaller acceleration there, 0.44. Not sure what happened that other time, but if we do this over and over with additional masses, we're seeing that the acceleration does go down. And if you were to plot this, you would hopefully see an inverse relationship there. Before we get to Newton's first law, I just want to show you that we actually even have a very quick way to do this experiment because this is something that's going to take a lot of time. I mean, you probably would take actually a couple of class periods to do a proper Newton's second law experiment. But in SparkView, I'm going to go ahead and start a new experiment again. Okay, we're going to go ahead and look at this Newton's second law quick start experiment. So this one uses the built-in acceleration sensor, I think, or no, it's just regular acceleration, excuse me, and also the force sensor on the y-axis. So if I go ahead and I'm going to zero my force sensor out, let's take a look here. If I grab onto the hook and, oh boy, that was a bad start. Let me try that again. All right. We see a linear relationship there between force and acceleration. And if we do a linear fit, I know it's very small. I'm not sure how well I can read that, but it shows m is equal to 0.244, the slope. Well, the mass of this cart is about 250 grams. Looks like we have a correlation there. Let's try this one more time with the mass. Let's see if the mass behaves this time. All right. Let's see if that slope changes. Let's compare it to the previous run. Hey, it did change. What do we have for a linear fit? Oh, about zero point 0.5. Well, this is 250 grams. 250 plus 250, 500. I think we're seeing a relationship here. So That's a nice way to do a quick Newton's second law lab if you wanted to. All right. Wow, we're actually at time, but hey, we'll go ahead and do Newton's first law real quick. This is not going to take us too long. Okay, I'm going to start a new experiment one more time. Let's give you another view. We'll start with a clean slate. And for this one, I'm only going to look at velocity because Newton's first law, would talk about what happens when the forces are balanced. There are forces on here. We talked about that earlier. Okay, so if the forces are balanced, what effect does that have on the motion? All right, let's see. All right, no motion. Okay, yeah, confirmed. Good thing we have those sensors, right? Okay, well, that's not very interesting, right? Because there's also two parts to Newton's first law. Because you have an object at rest, staying at rest, but what if it's in motion? What is going on with that motion? So let's see if I just give it a nice little push. Oh, hey, look at that. I mean, that velocity is staying relatively constant on there. I mean, there's a little bit of a slope because of friction, but compared to what we saw before, we're not really seeing a change in velocity. There's no acceleration. I'm going to just take a look at the acceleration graph. So you can see here's my initial push. And when it came to a stop, yeah, but the acceleration is basically zero. Came off the track there. Pretty cool. So that was a lot of stuff that we covered. Um, I'm going to go ahead and show you some resources that you can access from the PASCO website. So here's the experiment library. Let me just reset that so you can see it again. I'm going to put in smart carts and filter, and then this shows you all of the labs that we have for the smart cart, and there's quite a few in there. If you want to search for things that have to do with Newton or Newton's laws, I just put in Newton. There's Newton's second law. There's a lot of Newton's second laws labs here, but you can see there's a one for Newton's first law, which goes a little bit more in depth than mine does, and a couple of Newton's third law labs. If you have any questions regarding today's webinar, feel free to reach out to us. We do have the chat, as you can see down here, and also you can. I think we have an email that's going out that you can also reply to. So those are your options. And also, we're going to stick around if you have any extra questions. Feel free to put it in the chat. But otherwise, thank you for your time, and I hope you found this informative.